Hello everyone. So today's video will be finding derivatives using the chain rule, but in particular we're interested in multiple compositions. So as you know, the chain rule, if you studied it already in a calculus class, is the rule that you use when you're taking the derivative of a composition. And much of the time you have varying degrees of difficulty in whichever class you're in. And with the universal thing that I've noticed is that you'll usually do a chain rule involving multiple compositions. So for example, here I have find w prime of x for w of x equals cosine of natural log of 4x squared plus 1. So you really have one function that's, lack of a better word, inside of another, composed with another one really, and you have another one that's inside of that. So specifically what I mean is 4x squared plus 1 is inside of ln, and ln of 4x squared plus 1, all of that is inside of cosine here, okay? So it's three compositions. Now, today what I'm going to be doing is I'm going to be going over basically how to maybe compute these, make it easier for you. So let me go with the first option. So I wrote option 1, which says f of g of h of x all prime equals, and I'll get to that in a second. But the first option kind of relates to how we traditionally see the chain rule written out, which is a composition of functions f, g, h, whatever. And I only wrote, there's three functions here involved, but this could be with 4, 5, whatever number of functions are composed. And the way this would work is, the way I'm going to do is I concentrate on the actual chain rule and the way it looks when you're looking at it in many classes. So for example, if I do f of g of h of x prime, I'm going to take the derivative of the outside function, which is f, and then I'm going to take f, which is f prime of g of h of x times the derivative of the inside, but the inside is another composition. It's g h of x prime. So when we find the derivative of that, this would equal, let me just write down what I have on top, write that down. The derivative of g h of x would be the derivative of the outside g prime h of x composed with the derivative of the inside, okay? That would be your derivative, okay, according to the chain rule. And the idea here that I want to look at is, notice how you're taking the derivative of the outer function with what's inside of that times the derivative of the next function in line, as say the next layer, with the function inside of that, times finally the derivative of just the final function on the inside. Okay, so how do I apply this here? So with my notation here that I'm using, I would call this h right here. This would be h. This would be my g function, ln, and then cosine would be f, okay? So that's how I would identify it. Now, I'm not actually going to label f, g, and h explicitly, write them down, and take the derivative of those individuals. That's not the point. You can certainly do that according to the chain rule too, but I'm kind of going for a shortcut today, and here's how that shortcut would look. So as I said, I'm going to start with the derivative of the outside. The derivative of cosine is what the outside is, f. So the derivative of cosine is a minus sign. So then you're going to take the derivative of cosine, but you're going to leave what was inside of the cosine all by itself with the derivative of cosine, which is a minus sign, times, now you're going to go to ln. And you're asked, so what's the derivative of ln? Well, it's 1 over x, right? So it'd be 1 over, but not x. You put what's inside of the ln originally there. And then finally, h prime here. So h prime is the derivative of 4x squared plus 1, which would be 8x. And that would be your answer. You know, I don't care about simplifying in this case. I know that doesn't look all that great, but we're not concerned with simplifying. That would be it. So the idea here is you're breaking down layers. You take the derivative of the outermost function, and you leave whatever was inside that function took the derivative of inside of the derivative. That's the inside of the derivative. And then you go on to the next one. The next layer here to cut down on here is ln. And we take the derivative of that function, 1 over x, but instead of x, we keep what the inside is here, and then finally we take the derivative of that inside. So each part gets a derivative taken of with the inside of the other one in there. Now the other way to do this, option 2, is as follows. I'm going to make up some functions here. I'm going to call the first function I for inside, m for the middle, and then o for the outside. I here stands for like the innermost function you see, which is 4x squared plus 1. Okay? M is the function, the next one outside this inner one, ln. But what are we doing? We're taking the ln of 4x squared plus 1, but 4x squared plus 1 is I, so you're doing ln of I. And then finally, O stands for the outermost function, cosine. But what am I doing? I'm taking the cosine of ln of 4x squared plus 1. So that is m, okay? Because that's what I was calling ln. And the way this way works is as follows. In fact, instead of O, let me pick a better letter here. Let me call this W. And the reason for that is because that's what I was calling that W. You don't need to actually do that, but it cuts down on the confusion. Let me just use the same variable I'm calling the whole function as my last one. So then, what I'm looking for at the end of the day, I'm looking for dw dx. Okay, so I'm using that quote-unquote Leibniz notation, the fractional notation for derivatives, or well, some people say it's like that fraction, but it's not really a fraction. Well, anyways, here's how this works. Well, for me to get from W to X here, first of all, you have to get from W to M, so dW dm, and then M relies on I, so you have to take the derivative of M with respect to I, and then finally I to X, okay? So, and if you notice as well, notice how this isn't actually happening. These expressions, if you think about them as fractions for a second, the di and the dm, they cancel, and all you have left is dw dx. So it kind of tells you if your order is correct or not. Okay, so again, you start with any variable to be the inner function, and then you make up another letter, and that represents the next function, but with the last variable, the I, in it. And last but not least, the outermost function in terms of the previous variable, okay? And yeah, and for the derivative, the idea is like you're going from W to X, but you gotta go through M, you gotta go through I, and then you can go through to X here, okay? So it's like paying the middleman here. Yeah, I wanna get all the way to X, but M and I are in the way there. You have to pay them. And payment is a derivative here. So dw dx is going to equal the derivative of each of these. Cosine of m is minus sine of m. Dm di is the derivative of m with respect to I. That's the 1 over I. And then finally di dx is 8x. Okay. So the only issue now is this is not in terms of x. So what I'm going to start doing is I'm going to start replacing each of my variables that I see with what I let them equal. So m was ln of I. 1 over I was 4x squared plus 1. I was 4x squared plus 1, so we put that in. And then 8x. And then finally, the ln of I itself is 4x squared plus 1, so I'm going to put that in. So at the end of the day, if you use this method, you got to remember that you have to write everything back in terms of what the independent variable was originally. And that is done by taking your derivative and replacing each of the variables, let it equal. Now, from my history as a tutor, I've noticed that some people kind of prefer one way over the other. Most people kind of prefer the first option because they find this notation that I just wrote here for the second option kind of tedious. They don't like writing out all the functions and such. I think this option number 2 is a little more organized and a little more mechanical in a sense. So that's one of the advantages that I see about it. But as I said, most people prefer the first option because of kind of saving on the writing and the organization. The first method, if I had to say if there was any downsides to it, you're sort of keeping track of what the outside is, what the inside derivative and such, so be aware of that. Now, both these methods, though, they have shortcomings, okay? So, like any method does. But for example, if you had r of x equals the square root of cosine of x cubed, you could rewrite this as x plus cosine x cubed to the 1/2. And if I were to use let's say the first method, if I was to take the root of this, my outer function would be like x to the 1/2. So I put the 1/2 down, plus x cosine x cubed to the negative 1/2. So I subtract 1. Now take the root of the inside. And it seems like, oh, that's great. It seems like you only have one whole inside, but careful. The inside is just a simple x plus the cosine x cubed. The cosine x cubed is actually a composition, so you have to use a chain rule there, okay? So it's not technically like a nested composition, a multi-composition one, so because of that x, that kind of ruins it. So how would I do the derivative of that? Well, I would apply the chain rule as the derivative of cosine, which is a minus sine of x cubed. So the derivative of the outside would be minus sine, and the derivative of the inside would be 3x squared. And I'm sorry, I'm running out of room here. Bring that big, but 3x squared here. Okay. And that's what you would have as your derivative. So yeah, that function doesn't play along kind of what I said. However, I think the first option for sure gives us a way to look at that and find the derivative of it, not like easily, but, a standard way, I guess you can say. Easy enough. Yeah, the other method where I write functions out, that wouldn't work out too well for option 2. Because what would I call I, what would I call M, etc. So it's doable, but it's not the easiest thing in the world. That's what I'm trying to get at here. So just be aware that there are shortcomings to every method that you use in math. You might find it easy for a big host of functions, but there are some functions where that's not going to work out really for you that well. Okay, so just keep that in mind, but I hope this does help you out, that you can apply this in a lot of other chain rule problems. Well, thank you for your time. Hope this helps.